In our very first lecture, one of the things that I provided was the definition of chemistry. And we basically said that chemistry is the study of matter. And we looked, I don't want to say in depth, but we kind of gave a little cursory glance at that in our first two units. And the other part to that, though, is it's the study of matter and its interactions with other matter and energy. And it's kind of that second half of the statement that we're going to start diving into in this chapter, specifically how matter interacts with energy. Matter is pretty concrete. I mean, we basically defined it as anything that occupies space and has mass. Um, Energy is a little bit more abstract. Because energy has no mass and can't be contained in terms of volume. And in fact, if you take physics or if you have taken physics, the formal definition that's given for energy is it's the ability to do work. And another aspect of energy is that it can transfer from one thing to another. And we're going to look at that interaction between matter and energy in the beginning of this chapter. So the one type of energy we're going to be looking at a lot is light. Now, that does include the light that we see, but it's going to include so much more. Light is also known as electromagnetic radiation, or abbreviated EMR. And this includes the light we see and then a whole lot of what we don't. In fact, the light that we see, what we call visible light, is just a very, very, very small part of the electromagnetic radiation. Now, the way that light interacts with things is is a flow of energy through the electromagnetic field, or what is called EM field. And the way it does this is in the form of waves. And this is really similar to an example that you have probably seen, like waves on a beach. Okay, so you have a wave, I'll make it blue for water. So you got a wave, and eventually that wave hits the beach. And as you're watching this, what you're watching is energy disturbing the molecules of water. That's why you can put something on that. Well, let's draw a little sailboat here. So there's a little sailboat. And you can watch that sailboat go up and down with the motion of the waves. So it's energy moving through water. Now, what is light moving through? Light is the interaction, as I said, with the electromagnetic field. And this is kind of an example here of what that field looks like. You have the electric portion of it, which kind of runs up and down in this respect. And then you have the magnetic field, which runs perpendicular to the electric field. And the kind of important thing to note is that you can't describe waves like you do matter. So waves have a different set of properties. Waves have different mathematical ways to be described that are different from matter. And one interesting thing to note about light is that light moves fast. Okay, well, how fast is that? The speed of light is 2.998 times 10 to the 8 meters per second. Now, if I write that number out, it kind of looks like this. One, two, three, four, five, six, seven, one more zero. So 298,800,000 meters per second. Now compare that to sound. Sound moves 340 meters per second. That's why when there's a thunderstorm, you always see the lightning before you hear it, because the light travels much, much quicker than the sound does. So what is the electromagnetic spectrum? The light that we see, the visible part here, is a very small portion. And you have probably interacted with or have heard about or experienced most of the forms of electromagnetic radiation without even knowing what they are. You can kind of look at some of these pictures here, but most of us have had X-rays. Most of us have experienced ultraviolet light anytime we go out in the sun. Um, Infrared light, is operating or is the part of the EMR spectrum that TV remotes work on. Um, the microwave portion, I mean, we've all heated stuff up in a microwave or we use our cell phones. And then there's radio waves at the end of that. Most of us probably haven't experienced gamma radiation. You don't ever want to do that because that's very, 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 very high energy. I mean, maybe, I don't know, was it Bruce Banner, the Hulk in Marvel? Sorry, kind of a nerd joke there. But anyways, um, so this is the electromagnetic spectrum. Now, how do we distinguish between these types? I mean, we label them, but what is the difference between them? What makes them have a certain region? And the way that we distinguish them, so we distinguish forms of electromagnetic radiation by what's called wavelength. We use the Greek symbol lambda. Now, what is wavelength? Let's compare two waves. Wavelength is just simply the distance between the tops of the two waves. So it's the top of one wave to the top of the next. That wavelength can be short. That wavelength can be longer. And if you look back at this EMR example, you can see the wavelengths go all the way from like 10 to the third meters down to 10 to the minus 12th meters. And the length of that wavelength, pun intended, um, determines where that particular form of light falls on the EMR spectrum. Now, and another important thing to note is that the higher the wavelength, the lower the energy. There is an inverse relationship between wavelength and energy. So something that has a low wavelength will have higher energy. Now let's take just the visible region as an example. So we've all heard the acronym ROY GBIV for like, the colors of the rainbow. That's the light that we see. So red, orange, yellow, green, blue, indigo, and violet. Red is on the higher end of that wavelength. And so red is the lowest energy color of the visible light spectrum. And violet has of the visible light has the lowest wavelength, so it has the highest energy. And if you think about it, like what comes after violet? Well, ultraviolet in terms of energy. And UV or ultraviolet light is what we try to avoid massive amounts when we're out in the sun, because UV light has enough energy to mess with your DNA and cause cancerous cells to form. The visible light doesn't have that energy, enough energy to do that. And it's the same thing with like X-rays. Keep on going down the energy scale here. X-rays, getting an X-ray here or there, not a bad thing. Getting a lot of X-rays, like thousands of them all at one time, not a good thing, because those X-rays have a lot of energy in them capable of causing damage, to things as small as your DNA. And definitely with like radioactive materials. Radioactive materials have so much energy, they're capable of not only damaging you on the genetic level, but physically damaging your skin and organs and damaging you on like the macro scale. Now, what is some ways that we measure waves? One of the ways is to measure its frequency. Frequency is the number of crests that pass through a point in 1 second. Frequency typically has units of hertz. We use Hz as as the shorthand for that, which hertz just means cycles per second. And we use this kind of weird looking V. I'm trying to redraw that a little bit better. So the top's got little tails on them. And here's kind of a comparison of of different waves that have different frequencies. So notice this top wave here. We got there's one wave, and then there's the second wave, and then the third crest. So we got one, two, three. So we would say that that wave has a frequency of 3 hertz. And then the next wave here, you can kind of see, well, there's 1, 2, 3, 4, 5, 6 waves, 6 crests pass through the same point in the same amount of time. And so that has a frequency of 6 hertz, and so on. You can kind of see, can you see the relationship here between frequency and wavelength? Just kind of look at the distance between one crest and then how many crests were able to pass through that point in 1 second. Here we see that frequency is inversely proportional to wavelength. In fact, we can do a mathematical relationship between frequency and wavelength. Frequency can be found by taking the speed of light. We use the letter c for the speed of light divided by wavelength. Or you can rearrange this equation and find wavelength by multiplying or by doing the speed of light divided by the frequency. But either way, the important thing to note here is look at where frequency and wavelength are in these formulas. You have one on top and one at the bottom of a fraction. That means it's an inverse relationship. So let's put all these things together that we have so far. A high wavelength means there's a low frequency and low energy. A low wavelength means high energy, I'm sorry, high frequency and high energy. Now, the other type of way that we measure waves is not necessarily the distance between crests or how fast they travel through a single point, but how tall is the wave? We call that amplitude. So you can look at it as kind of like how tall is the wave. Now we're kind of assigning like a physical characteristic to something that doesn't have a physical nature. So I'll give you a little bit more of a formal definition, but how tall is the wave? But another way to look at it is it's the measure of the disturbance of the wave. Here's how I want you to think about amplitude. Let's say you have a light switch that's on a dimmer. When you turn that light on, it emits the same color. But if you turn the dial all the way to max, that color gets more intense. So you kind of think of it like brightness. So if you have a blue light and it has a low amplitude, it's not super bright. But if it has a high amplitude, the wave is high. It's still the same wavelength, it's still blue. It's just the amplitude's higher, so it looks brighter. Think of this also in terms of volume for sound. Sound travels in waves. It's the disturbance of matter through air. And so if there is a very soft sound, maybe you have your radio turned down, then the wave is still the same. It's just a low amplitude. You turn the dial on your radio to turn it up, and you're increasing the amplitude of the wave. It's still the same exact sound, still same sound wave. It's just the amplitude is higher. Now, all of this, interaction of waves with matter was pretty much the conventional thinking until Einstein came along. And you'll have Einstein to thank for, the weird things that we're going to talk about on the subsequent pages. But Einstein had theorized and had done experiments that shown that light can act sometimes as a particle as well. This was known as the wave particle duality. And this led to a new branch of physics called quantum mechanics. Now we're going to do a very, 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 very light cursory view of quantum mechanics simply because it requires a high amount of intense and advanced calculus that we're just not going to go through in this class. And that's not something that you will need to worry about in this course. But there are some aspects of quantum mechanics that can be grasped in a cursory manner without having to go into those I'm sorry, those complex concepts. So I talked about amplitude on the previous page. Now, before we get into discussion of quantum things, let's talk about what happens when waves interact with each other. We call this wave interference. Wave interference is just waves bumping into each other or interacting with each other. Waves interact in two ways. There's constructive interference and destructive interference. Constructive interference is when two waves interact and they have the same wavelength and they're in phase with each other. Now, what do I mean by in phase? The crests line up, the valleys line up. So same wavelength, and they are in phase. And what that has is it's an additive effect. It causes those waves to have the same, it still has the same wavelength, but the amplitude is bigger. Now you can imagine what destructive interference is. It's kind of the opposite effect. So again, I'm going to use two waves that have the same wavelength, but they're out of phase. So notice how the the peaks are not lined up, the valleys are not lined up. So same wavelength, but out of phase. And that kind of has a subtractive effect where basically it nullifies, they cancel each other out. So one kind of example of this, I'm a musician, and so there are like maybe when you're at, say, an outdoor concert, and there are sometimes when you're walking like far away from the stage, from all the speakers and amplifiers, you can kind of do an arc around the venue, and you notice that like especially if the sound isn't done properly, the speakers aren't properly placed, you'll notice that there are portions where the sound is a lot louder than other places because that's the speakers, the waves that are coming out are constructively interfering with each other. And there might be even places where the sound is deadened, where it's like super soft because the way the waves are interacting, it causes destructive interference, and those waves are canceling each other out. Now, let's kind of jump into the quantum realm. And when we talk about the quantum realm, the reason we have to have this discussion is because matter on the large scale doesn't behave the same as matter on the small scale. And we have two different types of physics or explanations that we can talk about in terms of macro and micro. So classical physics helps us explain everyday life. Like, for example, gravity. Throw a ball up, it comes down. We can see that. We can do equations to kind of describe the effect of gravity. But quantum mechanics is what we use to explain small scale physics. Like, for example, let's look at this cat picture. Now look at the whole picture. Okay, think of that, think of the whole picture as classical physics. We can kind of see the curves of everything. We can see the individual, hairs on the cat, the whiskers, the nose. We can see things detailed. But if we were to zoom in, kind of like on this little small portion here, what do we see? We see pixels. These things are just individual little squares. Those little individual squares aren't the curves, the hairs, or anything like that. It's the quantum mechanics behind this picture. And the key thing to note is that at the small scale, at the quantum scale, stuff behaves weirdly. I know that's a technical term, but stuff at the small scale does not act like stuff at the large scale. And here's kind of an example of this. So this is an actual experiment that was performed. So this is known as the double slit experiment, where in one experiment, a bunch of electrons or a handful of electrons or particles, I should say, were fired through a barrier. This barrier had two slits in it. And so you can kind of imagine some of these particles are hitting the barrier and some of them are getting through. And so when scientists fired actual particles, it would create two regions of where those particles would impact. So this is, you know, the way matter should act, particles. In a separate experiment, again using a double slit barrier, scientists would fire waves through through this barrier. And you can kind of see a single wave passes through the barrier. So when it passes through this one, it creates, I'll use a different color here. It creates a new wave. And when it passes through the second opening, it creates a second new wave. And those two new waves interact constructively, destructively, and you get this kind of continuous spectrum as the waves impact the screen. Okay. So again, I want to emphasize we have things acting like particles. Yeah, that's what we'd expect. This is what we would expect for waves. Now, here's kind of the weird thing that happens. When electrons were used, if a massive number of electrons were fired into this double slit barrier, so that represents this experiment on the top. So here are a lot of electrons. They're fired into this double slit. Look at what resulted. Notice there isn't just two patterns like up here. They're spreading out. You're getting multiple, like a spectrum of electrons hitting this. That looks a lot more. What does that look more like? That looks like a lot more like the pattern we would see if waves were going through the double slit. Here is that example of stuff acting weirdly at the small level. Because we think of an electrons we think as a particle. I can write that better. So we think of electrons as particles because they have mass, they have a charge, they're physical objects. But in this experiment, maybe they're waves. But here's kind of the weird thing. If we fire a few electrons through this double slit experiment, we get what we would expect to have happen. Something like this. If we fire a lot of electrons, then we start to see electrons acting like waves. So big particles act like particles. Small things like electrons act as both a particle and a wave, going back to this wave-particle duality. So again, I want to emphasize the small world, the quantum world, is weird. We can't use the same descriptions of macro objects. We can't always directly apply them to the small scale, to things like electrons, as this double slit experiment emphasizes. Now, one aspect of quantum mechanics that we are going to talk about, we don't need advanced math, advanced calculus to talk about this, is what's known as quantization. Quantization is just what that simply means is that only certain values are allowed. Now, what do you mean by values? Various traits for very, very, very small objects. Here's an example of quantization. Let's imagine we have built a ramp and we have a ball. We can put that ball anywhere on this ramp. We could put it there, we could put it there, or we could put it there, or we could put it there, and so on and so forth. This is what classical physics is what we're allowed to look at, or what is known as continuous, because we can put that ball anywhere. Now, if we take that same ramp, we're going to zoom in. What we find in the small scale in the quantum world is we don't find it's a ramp. It's actually more like a staircase. And if we take that same ball, we could put that ball here, or we could put it here, or we could put it here. But can we put it there? No, we can't. We cannot put the ball where, the boundaries of the stairs are. And so in this case, where the ball goes, we would say is quantized. It can be here, it can be here, but it can't be there. There's only certain values, certain locations where that ball is allowed to sit. And we're going to take this concept of quantization and apply it to the model of an atom. So what we're going to be looking at here is what's known as the Bohr model of an atom. So Niels Bohr was a scientist who proposed the model for an atom and how the electrons are arranged. So he basically said you got your nucleus. And around that nucleus are regions known as orbitals. So that's our nucleus. And that little dotted circle, is known as an orbital. Electrons can only be located in an orbital. So there's an electron right there. That electron cannot be here, or here, or here. It can only be in that orbital. Now, atoms have multiple orbitals. Think of this model as like a hotel, electron hotel. So you have a first floor. That's where an electron can be. There's a second floor, and you could put an electron there. But you can't put an electron in the middle of a floor. Just like you can't reside, if you go to a hotel, you can't be on a 1.5 floor. You're either on the first floor or second floor, or you're on the third floor, and so on and so forth. So electrons can only be located in these orbitals. This is the quantization aspect of it. It's either in one orbital or it's in another. It cannot be in between. Now, if a certain amount of energy, a fixed amount of energy, is supplied to that electron, it can cause that electron to go to another orbital. But again, it has to have a right amount of energy to do that. If it's not exactly the right amount of energy to go to another orbital, it doesn't happen. And when that energy, or I'm sorry, when that electron, quote unquote, relaxes, when it loses that energy and goes back to its original floor, it lets off that energy in the form of light. So a key thing to get about the Bohr model of an atom is each orbital is higher in energy the farther away from the nucleus it gets. These, and I'm going to refer to them as energy levels, are quantized. Meaning, as I said before, an electron can be on that first orbital, or it has to be on the second, or it has to be on the third. You'll never find an electron here, or here, or here. It always has to be on one orbital or another. Now, one of the ways that this is proven is using something known as the hydrogen emission spectrum. So if you excite a hydrogen atom, what is noticed is that there are different wavelengths of light that are emitted. So again, we're going through that process of we take an electron, give it energy, and it goes to another orbital. And then when it relaxes back to the original orbital, it emits energy in the form of light. How far that electron gets from the nucleus corresponds to a particular, I'm going to use a different color here, particular wavelength of light. Now, on this diagram here, what we have is a hydrogen nucleus, and then the various orbital levels for an electron. So let's just put an electron here, and I'm going to call it n equals 1. Now, an important thing to note is the distance between subsequent orbitals. Each new orbital, or each higher orbital, is higher in energy farther away from the nucleus. So I kind of said that on the previous page. But the distance, I'm going to put this in quote because not really like a length, but the distance from each consecutive orbital decreases. So let's pretend, for example, we take this electron and it gets excited up to n equals 2. Notice that distance there is smaller than if we were to go from, say, n equals 3 to n equals 4. So the farther away an orbital gets from the nucleus, yes, it goes up in energy, but the distance between one orbital and the next one decreases. So if we were to kind of look at just some general trends, the change in energy from orbital 2 to orbital 1, that's a bigger gap than the change in energy going from orbital 3 to 2. That's bigger than the change in energy. Sorry, I forgot the E there. From 4 to 3. And so on and so forth. I mean, we can keep on going to technically infinity, but we're not going to do that. If I put this kind of like on a graphical scale, let's imagine we have increasing energy here, and we start at n equals 1. And then we go to the next orbital, n equals 2. Now to get to n equals 3, that distance is a little bit smaller. And then to get to n equals 4, that distance is a little smaller. And then 5, it's even smaller than that. And so on and so forth. And so going from 2 to 1 is less, requires less energy or releases less, more energy than say 3 to 2. Or going from 5 to 4 releases less energy than going from 4 to 3. So let's put this all together and take a look at this problem. So which of the following transitions would absorb the longest wavelength of light? Okay, now you notice I never said anything about wavelength here, but I did talk about energy. So let's go all the way back here to the beginning when we were talking about energy and wavelengths. There's an inverse relationship between wavelength and energy. So let's go to our problem here. Longest wavelength, so high wavelength means low energy. So we want to find which of these transitions, so let's draw our graph here again. N equals 1, n equals 2, n equals 3, n equals 4. So which of those transitions requires the least amount of energy? Okay, well, let's just kind of notate both of them. So letter A is going from 3 to 4. Okay, so that's that right there, that little red arrow. Kind of zoom in right there. Okay. Then B is 1 to 2. So B will be the blue arrow. And then C goes from 1 to 3. So I'll use a green here. So here's 1 to 3. And then D is going from 2 to 4. I'll use orange. 2 to 4. Now, just by looking at the lengths, we don't have to do, we can do some math, and then I might, I'll show you a little bit about how you can do this mathematically. But just by quote unquote looks alone, what is the smallest energy transition? Well, that would be from 3 to 4. So that's the lowest energy, which means that will have the highest wavelength. So the transition from 3 to 4 will be that will have the longest wavelength because it has the lowest energy. All right, that's where we'll stop with this lecture. I will have more posted very soon.